In this episode, we take a topic that often feels invisible and turn it into something you can reason about clearly. Domain name system, DNS, and name resolution, which is the process that turns human-friendly names into the network destinations computers actually use. Many beginners think DNS is just a phone book, and that comparison is not wrong, but it misses the security problem. If an attacker can influence name resolution, they can redirect trust without breaking into your systems directly. A user can type the right name and still land on the wrong destination, and a workload can request the correct service name and still be pointed at an attacker-controlled endpoint. DNS also creates a quiet trail of activity that attackers can use to hide access, because name queries can reveal what systems are trying to reach and can be manipulated to blend into normal traffic. Securing DNS is therefore not a niche networking detail. It is a foundational defense that protects identity, encryption, and routing from subtle redirection. When you understand how name resolution works and how it can be abused, you can build controls that keep trust anchored to the right destinations. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A solid mental model for DNS starts with recognizing that computers do not truly talk to names. They talk to Internet Protocol. IP, addresses, and names are just the user-friendly layer that gets translated along the way. When a client needs to reach a service by name, it asks a resolver, and the resolver responds with an address that the client uses to connect. Beginners sometimes assume that the resolver is always correct because it is part of the network, but resolvers are systems that can be configured, misconfigured, compromised, or replaced. That is why name resolution is a security boundary, not a neutral utility. In cloud environments, there may be multiple resolvers in play, including provider-managed resolvers for private networks, enterprise resolvers, and public resolvers, and the choice of which one is used affects both security and visibility. If an attacker can influence which resolver a workload uses, they can influence where that workload connects. Securing DNS means making resolver choice deliberate and enforcing it in ways that are hard to bypass. Trust redirection is one of the most important DNS risks to understand, because it is surprisingly powerful and surprisingly easy to overlook. If an attacker can return a malicious address for a legitimate name, they can route traffic to a destination they control, potentially capturing credentials or delivering malicious responses. Beginners often think encryption solves this, but encryption only solves it if the client correctly validates the identity of the server it connects to. If clients are misconfigured to skip validation, or if they accept weak trust signals, redirection becomes far more dangerous. Even when validation is strong, redirection can cause denial of service by sending traffic to unreachable destinations, which can disrupt operations. Trust redirection can also be internal, not just external, where a private service name is pointed at an attacker-controlled instance inside the network. Understanding this risk helps explain why DNS is tied to identity and encryption, because name resolution is one of the first decisions in the connection chain. Caching is a core feature of DNS that improves performance, but it also introduces security and troubleshooting complexity that beginners should understand. Resolvers and clients often cache answers for a period of time, defined by a time-to-live value, so they do not need to ask repeatedly. Caching can help an attacker if they successfully inject a malicious answer, because that answer may persist until it expires. It can also frustrate defenders when changes are made to fix an issue, but clients keep using old answers. Beginners sometimes interpret caching behavior as randomness, when it is actually predictable once you understand that answers are stored temporarily. Securing DNS includes managing caching behavior thoughtfully, especially for critical services, so that legitimate updates propagate and malicious persistence is minimized. It also means understanding that DNS answers are not always real-time reflections of the current truth. When you plan for caching, your security controls become more reliable and your incident response becomes less confusing. Another major risk area is DNS hijacking and poisoning, which are broad terms for manipulating DNS responses so that clients receive incorrect information. Hijacking can occur at different points, such as compromising a resolver, changing configuration that controls where queries go, or exploiting weaknesses in how queries are validated. Poisoning often refers to injecting false answers into caches so that many clients receive the wrong destination. Beginners do not need to memorize the mechanics of specific poisoning techniques to grasp the defensive lesson. If you treat DNS responses as automatically trustworthy, you create a single point of failure for many connections. Securing DNS involves protecting resolver infrastructure, restricting who can change DNS configuration, and using validation mechanisms that make spoofed answers harder to accept. It also involves monitoring for signs of manipulation, such as unexpected changes in name-to-address mappings for critical services. When DNS is protected, attackers have fewer opportunities to redirect trust at scale. Cloud environments introduce special DNS considerations because private name resolution is often used for internal services that are not publicly reachable. Private DNS zones, internal service discovery, and provider-managed resolvers can create convenient naming, but convenience must be paired with control. Beginners sometimes assume private DNS is automatically secure because it is not visible to the public internet, but internal threats and misconfigurations still apply. If a private zone can be modified too easily, an attacker who gains access could redirect internal service names to malicious endpoints. Another concern is split horizon behavior, where the same name resolves differently depending on whether the client is inside or outside a network. This can be useful, but it can also create confusion if not documented, and confusion is fertile ground for mistakes. Securing cloud DNS means treating private zones with the same integrity expectations as any other critical control, including access restrictions and change auditing. Name resolution is also closely tied to egress control because DNS queries often precede outbound connections and can reveal intent even when traffic is encrypted. If a workload starts resolving domains that are unusual for its role, that can be an early signal of compromise or misconfiguration. Attackers also use DNS as a stealthy channel, sometimes encoding information into queries or using rapidly changing domains to evade simple blocks. Beginners should not panic about exotic techniques, but they should understand that DNS can be both a tool for normal operations and a tool for attackers. Securing DNS includes logging and monitoring queries in a way that helps defenders see patterns. It also includes restricting which resolvers can be used, because allowing workloads to query arbitrary public resolvers can bypass internal visibility and filtering. When you control resolution paths, you gain both stronger policy enforcement and better detection opportunities. Resolver selection and enforcement can sound like a minor configuration detail, but it is one of the most impactful DNS security decisions. In a well-governed environment, workloads use approved resolvers that apply consistent rules, log queries, and are protected against unauthorized change. If workloads are allowed to use any resolver they choose, then a compromised system can intentionally switch to a resolver that is harder to monitor or that allows resolution of malicious domains you would otherwise block. Beginners sometimes assume that because a resolver is reachable, it is acceptable, but resolver choice should be treated like choosing where your security camera footage is stored. Approved resolvers provide a controlled point for visibility and policy, while random resolvers create blind spots. Enforcing resolver use can involve network rules that limit outbound DNS traffic to approved destinations, as well as host and platform settings that define resolver configuration. When resolver use is enforced, DNS becomes a managed layer rather than a chaotic one. Integrity of DNS data also depends on controlling who can change records, because DNS records are a form of configuration that can redirect traffic instantly. In cloud environments, DNS zones and records are often managed through control plane interfaces, which means they should be logged, monitored, and protected like other high-impact settings. Beginners should connect this to earlier lessons about control plane logging, because changes to DNS are configuration changes with security consequences. Good practice includes limiting who can modify DNS zones, requiring approvals for high-risk record changes, and alerting when sensitive names are altered. Another helpful practice is using naming conventions and ownership tags so that the responsible team is clear, reducing the chance of unmanaged zones drifting into risky states. When DNS changes are controlled and visible, attackers have a harder time using DNS as a quiet redirection mechanism. Visibility also speeds recovery because you can identify what changed and when. A beginner-friendly way to think about secure DNS is to treat it as part of identity, not just part of networking, because names are a form of identity for services. When you connect to a service name, you are expressing intent, and the system that resolves that name is deciding which endpoint will receive your trust. If that decision can be manipulated, then your security assumptions can be bypassed. Encryption helps protect the connection, but only if it is paired with proper validation, and DNS helps decide which endpoint is even contacted. This is why secure DNS and proper encryption configuration reinforce each other. When both are strong, attackers have a harder time redirecting traffic to imposter endpoints, and they have fewer options for hiding access patterns. When either is weak, the other can be undermined through misdirection and bypass. Logging and analysis of DNS events is one of the best ways to detect both accidental misconfigurations and deliberate abuse, because DNS provides a near real-time view of what systems are trying to reach. If a service suddenly starts querying unfamiliar domains, that behavior can be investigated before data is exfiltrated. If internal names begin resolving to new addresses unexpectedly, that can indicate an unauthorized change or an infrastructure drift event. Beginners sometimes think DNS logs are too noisy to be useful, but normalization and correlation strategies can turn that noise into patterns, especially when you know what normal looks like for specific workloads. DNS logs also help with incident response because they can reveal the sequence of attempted connections even if the connections themselves were blocked. When combined with egress controls, DNS visibility becomes a powerful early warning layer. Treating DNS as a monitored security signal, not just a utility, strengthens your defensive posture substantially. Securing DNS and name resolution ultimately means protecting the mechanisms that decide where trust is sent and ensuring that name-based access cannot be quietly redirected or hidden. You do this by enforcing the use of approved resolvers, protecting resolver infrastructure and configurations, and tightly controlling who can modify DNS records in private zones. You also strengthen detection by logging and analyzing DNS queries and changes, and by correlating them with identity, control plane, and network activity. For new learners, the key lesson is that DNS sits at the start of many connections, so weaknesses here can undermine otherwise strong controls like segmentation and encryption. When DNS is secure, names resolve predictably, traffic goes where it is intended, and unusual access patterns become visible rather than stealthy. That combination keeps trust anchored to the right destinations and makes it harder for attackers to hide behind the quiet, everyday machinery of name resolution.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.